So, welcome to the last session of today, to the talk about Type Erasure, the implementation details. So, I'm Klaus Iglberger. What I'm doing is I basically by now do trainings for a living, C++ training, C++ consultancy. And what I mostly do is I talk about topics like software design, also a little bit of architecture, mostly because nobody else is doing it. And so last year, at CPBCon 21, I've actually talked about Type Erasure, and I've talked about Type Erasure as a design pattern. I've shown people why this is actually a superior way of breaking dependencies, superior to the usual approach of using inheritance hierarchies. This was a hopefully good talk. Now this one is kind of a successor, because if you talk about design, you cannot so much talk about the implementation details. There's quite a lot that you can do, in particular, in context of optimizing performance. This is something that last time I totally ignored because 60 minutes is actually a very, very short time frame. This time I definitely go much more into detail how you actually can gain performance by using this technique. However, do not worry, you're not required to know this other talk. I will go into the details of what is Type Erasure and how to do the basic things again, because we have to see these implementation details anyway. So I will first talk a little bit about why to use Type Erasure. Then we'll see this basic Type Erasure implementation that I showed last time, although I already go a little more into detail because there's a lot of choices. And I'll start talking about what you can do to actually speed up performance. And of course, this is important and pretty interesting because C++, after all, is about performance. All right, and there's a second technique, Type Erasure with manual virtual dispatch. So why use Type Erasure in the first place? So let's assume that we have a function f here at the bottom. And this function f is supposed to be given a command, something that can be called. This can be something like a print command. This can be something like a search command, an execute command, something. Now, of course, this is similar to what we do in the STL2. In the STL, the algorithms take something that can be just called. But of course, you know that in the STL, everything is solved by templates. This is exactly what I do not want to have in this case. I do not want to have a function template. I do not want to have everything in the header file. I still want to be able to move my implementation details to a source file, hide those details. And so let's agree that we definitely want to be in the realm of dynamic polymorphism. If you do want to use templates, if you do want to use static polymorphism, then basically this is a totally different talk. We want to stick to dynamic polymorphism. And so we could have a base class, a command base class, many derived classes, and provide any of these derived classes. Anybody could write new classes. Anybody could therefore customize what is executed in F. Would you do that today? No, definitely not. What you would reach for pretty much right away is std function. Std function is so much easier on so many levels. First, there is no inheritance hierarchy, so it's way easier to actually write the stuff. It's non-intrusive, so you don't have to inherit from something. You have a lot of design choices because of that. There is less dependencies. That's the design aspect. You can just write what you want in a specific form. There's less pointers involved. There is no dynamic memory allocationing happening. You don't have to do a make unique or something like that. You don't have to manage lifetime. And it's a purely value semantics-based implementation, which is exactly what, I shouldn't say what modern C++ is about, but it's a huge part of what modern C++ represents. And altogether, you realize you have less code to write, and there's a potential for better performance also. So it's, in other words, just much cleaner code. This is now Type Erasure. Standard functions implemented by means of this technique, by means of Type Erasure. And I do not want to create the illusion that standard function is the only example here. So let's generalize this. Let's say we want to have a function that takes some kind of shape, and this kind of shape is, for instance, supposed to be drawn, serialized, or whatever you want to do with this shape. Of course, we could implement many shapes and pass them to this function f, which does something to a shape in general. Would we do this today? What exactly? No, again. For the same reasons. We would write a Type Erasure wrapper. call it shape, which just takes any circle, square, or triangle. Again, the advantage is the same. There's no inheritance hierarchies left. It's non-intrusive, so you can write a circle, square, triangle without having to worry about any base class. Therefore, there's less dependencies. There's no pointers on your side anymore. There's no manual dynamic allocation, no lifetime management by means of any kind of smart pointer. Again, it's a value semantics, less code to write, and potentially you've just improved your performance. So that's exactly what we want to do. We want to write this shape, this wrapper that allows us to deal with any kind of shape, anything that has a certain set of properties, and we want it to be faster. So how do we do that? However, inheritance is indeed rarely the answer. This is a quote from the Pragmatic Programmers from Andrew Hunt and David Thomas, who actually didn't wrote this about C++. They wrote this about software design and software development in general. And I think they truly meant that. And I'm trying to show you that perhaps type erasure is a better answer. Not always, definitely not always. Every tool has its disadvantages, but perhaps this is a little more what they had in mind. So let's take a look at the basic implementation. But first, what I'm now showing you is not a void pointer. It's not a point to the base, and it's not a stud variant. This is all things that some people have claimed to be type erasure, where they have used this term for. Now, what I'm now showing you is that type erasure is a wrapper, essentially, with a templated constructor, plus a completely non-virtual interface, and last but not least, a clever combination of a couple of design patterns that enable us to do all of these things in the wrapper. All right, and our toy problem is drawing shapes. And I know, that's not exactly the most fun example. It's not exactly rocket science, but to quote my colleague from the Munich C++ user group, I'm tired of this example, but I don't know any better one. So it's a super simple example, but because I'm showing you something that you might not have seen before, I believe it's a reasonable example. It's so simple that you can focus on the implementation details. And after all, that's the point. So let's start with writing circles and squares. Here, the circle class is a class that in the constructor may take all the things that make a circle, like a radius or a couple of other things. It may have a couple of getters for the things that make a circle, like the radius, a center point, perhaps even a rotation. And of course, there is a couple of data members. So it's a circle. Most importantly, okay, there's of course also a square, else the circle would be so alone. The square is pretty much the same thing. It just expresses all the properties of a square. Note, we don't need any base class. This is just the classes that we write, that anybody can write, that we'll later be able to add, to squeeze into this type erasure wrapper. And they also don't have to know about each other. This is totally disjunct types, totally unconnected. There is no dependencies whatsoever. And also, most interestingly, these types don't know about drawing. They don't know about serialization. They don't know about any potentially highly coupling operation. They're just totally unconnected, basic geometric primitives. So then how do I connect them? How do I write this wrapper? Well, I start with a separate class hierarchy. I start with a shape concept base class. And truly it is a base class. It comes with a virtual destructor. And this base class is inherited by a class template, which I call shape model. Shape concept and shape model, by the way, are pretty common names in this context. Can, of course, choose any other name. So shape model is a shape concept, but it's a class template also. And as a class template, this now takes any kind of shape. This can be circle, this can be square, this can be triangle, this can be any shape that you can imagine. And it stores one of these. So I now have a data member of, well, shape T. Of course, I also have the according constructor in order to be able to take one of those. Now, I want shapes to be drawable. I want shapes to be serializable, or whatever you can imagine. This is now affordances, or simply operations, that this base class formulates. like any other base class. So I have a do-draw function, I have a do-serialize function, and of course take a couple of arguments, whatever you need. The pure virtual, so obviously the shape model has to implement. And the shape model does implement these two functions by doing the thing that you want to do on a shape. So I serialize this object, I draw this object, whatever needs to be done. This is the place where we now actually implement the logic. Most importantly, however, we do not want to have draw or serialize within circles and squares. We want this to be separated. After all, this is one of the primary guidelines in software development, separation of concerns, the single responsibility principle. We do not want to have the dependencies within the object. So for demonstration purposes, I use a free function. This is quite reasonable. Now, so as I said, you define these affordances separately. Note the do. The do is because we have complete freedom and it doesn't have to be the same. But of course, in this context, I also avoid name collisions. If I have a draw function inside the call from inside, then this cannot be called draw also. This would definitely mess up name lookup. So I call it do draw. You don't have to worry about this later. Also, believe me, this doesn't mess up any interface. It will be an internal implementation detail. All right. This idea to have a separate, totally disjoint inheritance hierarchy, this is actually a design pattern. This is called the external polymorphism design pattern. A design pattern was proposed in 1996 in this particular paper. And the intent is to allow C++ classes unrelated by inheritance and or having no virtual methods to be treated polymorphically. This is a pretty beautiful design pattern because you can treat any type, and really stressing any type polymorphically. The type doesn't need to have virtual functions on its own. That's the beauty of this particular design pattern, which we'll make use of. All right, so the external polymorphism design pattern allows any object to be treated polymorphically, extracts the implementation details, that's the single responsibility principle, and it removes dependencies to all operations affordances because it separates this polymorphic behavior. Last but not least, you can now write your types, your circles, squares, etc. Totally unrelated. This is the easiest way to write new stuff. This fulfills this open-close principle. Okay, but back to the code. This now works. I now provide the affordances. I write the free functions that I now require. I write serialize and draw for circle and serialize and draw for square in any form. So this is the functions that I called from above. You just see it up here. This is exactly the function I call here. But please do not feel that this must be part of this hierarchy. No, this is elsewhere, separated. And there can be many forms. You can have one draw function that uses OpenGL, one that uses Metal, one that uses Vulkan. This is indeed where we split up the different possible implementations. All right, then is one function that goes over all possible shapes, shape concepts. Remember, that's the base class that contains all kinds of shape. I call the according draw function, and that will trigger either, of course, draw circle or draw square. The only thing left is to actually set something up that works. So I shorten the type a little bit. I have a vector of unique pointers of shape concept, and I'm creating the according shapes. So a shape model of circle is created. Pass a radius of 2.0, for instance. This creates the circle accordingly. And then I have the shape model stored as a shape concept and can polymorphically use circles and squares, although they do not have a base class. Now, I really provided this inheritance hierarchy separately, externally, external polymorphism. All right, but I know that you're not totally amazed right now because this is not beautiful yet. There's a lot of manual allocations. There is a lot of pointers still floating around. Sure, it's unique pointers. This is not quite as bad, but still, it doesn't look nice. It looks a little convoluted. Definitely, we'll clean this up and turn this into a value. This hierarchy, this external hierarchy, is simply put into a class. And this will be our shape wrapper. And that's the first thing you do in any type erasure wrapper. You kind of encapsulate this external hierarchy. Now, this class, the shape class, is given a constructor. And that's a absolutely necessary piece of a type erasure wrapper. You get a constructor that actually deduces some shape type. So it's a function template, this constructor. Takes any shape, takes a circle, square, triangle, whatever you have in mind, and directly creates the according shape model. You don't have to worry about this anymore. It's in implementation detail anyway. And it fills this into a unique pointer of shape concept, but now inside the class. And the name Pimple might give it away. That's now what we call the bridge design pattern. So we have many, many implementations, many shape models. For every possible type that you now feed into this, you have a new shape model. And all of these models can now be stored in terms of this pointer. And so if I put a circle inside, I store a pointer to this base class and have effectively erased the type. After this, after the constructor, I have no idea anymore whether I store a circle, square, triangle, or whatever. It's gone. The information virtually is gone. Type erasure, hence the name. All right. However, of course, I now want to use this. The type is not entirely gone. I have the according virtual functions in my base class. And so I simply provide the functions that trigger this polymorphic behavior. So this serialize function, for instance, triggers the do serialize function on the pimple. This draw triggers the do draw on the pimple, on the shape concept pointer. Not the friend keyword though. This is actually free functions. We call this a hidden friend. So it is a function that will be injected into the surrounding namespace, and it will be callable as a free function, but it is a friend after all. Therefore, it's perfectly allowed to use the private data member Pimple. And one of the huge bonuses of having this hidden friend, these two functions actually do not really add to the overload set of functions called draw and serialize. Only if you do have a shape, and only in that case, these two functions are considered. And so this may actually also improve compile time a little bit. Now they are used exactly at the point where we need them. All right. Now, this is actually already a type erasure wrapper. This works. We could go with this, but right now it is move only. Our data member is a unique pointer. And so at this point, what we could do is we could move shapes around. If this is what you need, if this is all you need, then stop there. Don't do anything else, because this is the simplest thing that you could possibly do. And hopefully you realize that so far this was about 20 lines of code in this wrapper, 25 perhaps. It's not a lot. It's actually quite a little. But very often, like for instance in std function, we want to be able to copy that thing. And so we have to deal with the copy operations in this case, because all we have is a unique pointer. So how do we implement copy? Which admittedly is a little bit of a challenge, because all we have is a pointer to base. We actually don't know what we have stored. The type is gone. So what we need is a classic solution that is introducing a clone function. And a clone function is something that you might recognize as yet another design pattern called prototype. The base class, the nested base class shape concept, introduces a clone function, pure virtual. I have no idea what I can do in a base class, but the derived class implements this clone function by creating a copy of itself. And for that purpose, I actually use the copy constructor. I pass asterisk this, which is something I seriously recommend. This will always be correct. Regardless of however this evolves, how the code changes, using the copy constructor will always do the right thing. Of course, given that the copy constructor is correct. But it's generated by the compiler. This is great. So this is actually the easiest and, again, most correct thing that it can do. So now, because of this clone function, we're actually able to get a copy. This is virtual copying indeed. So we can implement our copy operations by simply cloning. So I initialize my Pimple by simply asking the other pimple to clone itself. Please give me a copy. And then have an exact copy without even knowing what I actually have. As I said, could be a circle, could be a square, I don't care. I get an exact copy and I'm happy with this. And a copy assignment operator, I simply implement by the common copy and swap idiom, which I know some people are not super happy about. It's not the most efficient thing to do. But in this case, there is no other thing that we can do. After all, we have no real information on what it is, so we can only create a copy. But at least for those who don't like that, you can reduce this to a single line if you want to. It's still the same thing though. All right, now the move operations. Because I have now implemented copy operations, move's actually gone. Rule of 5, so I now also have to deal with the move operations. But interestingly, this is not just a little thing. There's a lot of choices. So the move operations can either be just defaulted. This is easy. So we can now move again. However, the consequence is, of course, that if you move from a shape, the shape now contains a null pointer, an empty unique pointer. And it means that if you move from such a value, and after all, we can copy this, we perceive it as a value, then suddenly this is something that results in a crash. Perhaps this is okay. Perhaps this is what you want. And actually, this is something that may be perfectly fine. But if this is fine, then probably also you want to add a default constructor, saying, okay, there is a default. This default is that it's empty. And a good example is, for instance, std function. You can create a default std function, but the std function is empty. And if you try to call it in an empty form, you will get an exception. Okay, this would not be as beautiful. You would get a crash, but still, perhaps this is semantically what you have in mind. Option 2, however, is that you do not define these two move operations. You actually do not touch them at all, which means these operations are totally gone. You do not have move, and the natural fallback is copy. So if all the shapes should always contain a value, if there is no null shape, for instance, then this is the right thing to do. Do not delete them, because then move would be an operation that triggers a compilation error. You want the copy operation instead. So basically replace the move. This is okay, but note as a consequence, the move operations are suddenly not no except anymore. So if you try to move, you will get a copy which right now does an allocation, and this allocation might fail, and therefore you would get an exception, which might not exactly be what people expect. So this is the two extreme choices. There's something in between that you can use, perhaps also to optimize performance a little bit. You could just forfeit the move constructor. Just say, okay, every Type Erasure wrapper needs a valid value. And so I have to create a copy in the constructor, but assignment could actually be implemented by simply swapping the implementation details, by swapping the unique pointers. If you do this, then at least the move assignment operator is no except, and fairly cheap and fairly simple without creating any other copy. Probably this is a nice compromise, but again, move construction, the move constructor is not no except. It totally depends on what you want to have. Is it okay that it doesn't have a value, or is it not okay? Okay. Fact, there is not the one solution that is always used. This is why there's also not the one implementation that we can use for everything. It's a design choice after all. Okay, draw all shapes now is updated. We no longer have a vector of pointers. We suddenly have a vector of values. Go over all the values and simply draw. And also the main function is updated, and suddenly it's becoming so much more beautiful. All we create now is circles, squares, other kinds of shapes, and we simply put them in a vector of values. Breathtakingly beautiful, absolutely. And so natural. I have a vector of shapes. What do I put inside? A circle. Of course, it makes sense. What do I else put inside? A square. And usually would be wondering, how does this work? But now you have an idea. That's the power of type erasure. So I have absolutely no pointers in the user code. Of course, inside the class, we agree there's a unique pointer, but you don't see that. I don't have to deal with pointers outside. I do not have to allocate memory outside. I never see a make unique. I never see a smart pointer. I don't have to manage lifetimes. This is done by my wrapper. It's truly value semantics, and it's very, very simple. On the using side, it is absolutely simple, and for that reason, definitely superior. It's kind of the KISS principle. Just to make Kate, the keynote speaker from this morning, a little happy, this is beautiful C++. So that's the basic idea. Just to give a quick idea of the design. At a high level, you have this wrapper, which is totally unaware of all the shapes. This is architecturally on a level below. This is where I have circles and squares, which also are totally unconnected. And only by putting them into the shape, I actually connect them. Provide this as an abstraction. The compiler, nice as it is, creates the necessary connecting code. So the shape model, the class template, is instantiated for all the different shapes automatically. This is code that you don't have to maintain. This is why it's so amazingly beautiful to maintain for you. Your life is so much easier. All right, amazing job. We have used Type Erasure to extract the implementation details of circles and shapes. There's no dependencies on anything there. We've still the ability to easily add new types, triangles, ellipses, rectangles, whatever you need. We've also separated interfaces, reduced duplication. We've pretty much removed all dependencies, nice. And we've removed all inheritance hierarchies, removed all pointers, manual allocations, and all kinds of lifetime management. Okay, it's inside the class, sure, but it's happening automatically. And we might have just improved performance. So now that's the point that I have to make. That's now what I continue to do. Why do we improve performance? So, truth be told, right now it's the basic implementation. It's nothing special. This is not really fast yet. So I should prove that by running a couple of benchmarks. However, performance. Performance is tricky. It really is. Now, if you stand in front of a crowd and mention performance, everybody starts to listen. And, of course, at least half of the people have something to complain about. This is the nature of performance results. So I'm going to present you a couple of performance results, but I only do this if you do promise me that you indeed just consider this to be qualitative results and that you do not take this too seriously. Your results will be different. So do you promise that? Okay, so I trust you. So here they are. I should explain first what I'm doing. I'm now having 4 kinds of shapes, which is definitely a little more realistic than just having circles and squares. I also added ellipses and rectangles, but of course there can be many, many more. I create 10,000 randomly shapes. Random shapes means that I do not have 2,500 of each of them, but approximately 2,500 based on the random number generator. But this helps me to make it a little harder for the compiler to do some optimizations. I perform 25,000 operations, and I've picked a cheap one. I've picked translate, which is smoothing the center point. I'm not doing this because I'm not really interested in drawing. Drawing would be expensive, and then all the solutions would have pretty much the same performance. Therefore, I chose something very cheap. And I'm benchmarking with all the compilers. I've run this a couple of years ago, 1 year ago approximately, and I'm using Core i7 with 3.8 gigahertz, up to 3.8 gigahertz. All right, so here they are. If you use a classic OS solution, which I pointed at in the very beginning, then this is the performance that we have. Clang turns out to be a little faster than GCC, but that's definitely not the main interest. The Type Erasure implementation that we have right now is exactly as fast. Exactly as fast. So this is actually good news at this point. Although we have built around this inheritance hierarchy quite a lot of stuff, this has no effect whatsoever on performance. Great. So we just gain a lot of beauty and a lot of maintainability without losing performance at all. But we now want to dig deeper. And this is we will now start to talk about what can we do to actually make it faster. There's a couple of options. Fascinatingly, because we do not have a pointer, we have a wrapper, we have a class. We can actually do a couple of things inside this wrapper that before were just totally impossible. So the first idea is that we just get rid of the allocation, obviously. Because right now, all I do every time is I always call make unique for any kind of shape I put inside. And you've seen that circles and square are kind of tiny things. There's not a lot inside. And still I put it somewhere on the dynamic memory. Not particularly efficient. So let's make it a assigned choice. Let's turn this into a class that never allocates. Of course, this is the other extreme. You can have something in the middle. But let's say that we never want to allocate dynamically. So now what I choose instead of a unique pointer to base is a std array of bytes. Okay, this starts to sound very low level, I know, but you'll see this is actually not super tough. However, please make sure that the alignment is fixed somehow. So right now, to make it to keep it simple at this point, I have a fixed buffer size and alignment within the class. This is not just a given. We'll talk about how to deal with this a little later. But I do have an alignment. I do have a fixed buffer size, a maximum. And this is now what I work with. Now, I do not really have a pimple anymore in the sense of I don't have a pointer to base anymore. But this array, this byte buffer, is now exactly what I consider to be my object. And this is the purpose of these two pimple functions. Yes, they convert, by means of a reinterpreted cast, the pointer to the first character into the shape concept that we had before. So here now called concept inside the class. Yes, I know, reinterpret cast. This does not make a lot of people feel very happy. This is something very suspicious. And it indeed is. Most use of a reinterpret cast are dangerous and not okay. This one, however, luckily, is totally backed up by the C++ standard. The C++ standard tells us that if there is something reasonable inside, we are actually allowed to convert this byte buffer, that's why it's okay, into the according object. And again, we don't know what it truly is. We only have a pointer to base, so we convert it accordingly. All right, the constructor. Okay, still, we have it's still, despite its implement a little differently, the bridge design pattern. But now, let's take a look at the constructor. The constructor is now responsible to create some object inside this buffer. So again, it's a function template that takes any type, circle, square, triangle, whatever, and it has to create the model inside this buffer. So in order to make it fit on the slide, I first shorten model of shape T to M. Excuse me for this short name, but you get the point, and it's only for a few lines. Then, also very important, I absolutely make sure that this actually works. I check the size of the given model. Does it fit into my buffer? If it doesn't, I get a compilation error. Then I also very important, check the alignment. Does the alignment actually work? If it doesn't, I get a compilation error. And only then I actually create, by means of a placement new, this model inside the buffer. So I pass the address of the buffer, so by means of the pimple function, to new, and I call placement new, created inside. All right. I still have shape concept and shape model. I still have. This didn't change at all. I've just changed the implementation details a little bit to accommodate the fact that I have this static buffer inside. So still, it's the external polymorphism design pattern. Nothing changed here. It's still the same thing. But the clone function has changed now. I do no longer return a unique pointer to base. No, I don't need that. What I now do is, I actually don't return anything, but I take a pointer to a piece of memory. So please copy yourself into this memory. That's what the implementation now does. So in the shape model, clone is implemented as copy yourself into this memory by means of a placement new. Again, it's a prototype design pattern, but this time in terms of this in-class piece of memory. Note that in all the places, in all the cases, I actually use ... new. I use the global placement new. There is people sometimes that actually overload the new operations in their classes. It is possible after all. And in order to be perfect, we of course want to make sure that we truly use the function that we actually intend to use, the real placement new. I know that this is a model that we have fully under control. It's in the private section, but please make it a habit. If you truly want to use the global placement new, if you want to avoid the class-specific implementations, then use the : new for that. Yeah, this is what you see a lot for very good reasons. All right. Suddenly, there's also another function called move. And the name gives it away. This is a function that does the equivalent of a move operation, just using this, this nested buffer. So the move operation also takes a pointer to some memory. And again, I'm using placement new, but this time I call the move constructor. So it's a beautiful equivalent, which now also allows us to efficiently move from one shape into another one. No efficiently lost at this point. All right. This is now the implementation details of the special member functions, which, first of all, start with a destructor, which now suddenly becomes necessary. All the compiler sees is a std array of bytes. And this is what it will destroy. Yeah, the compiler would simply destroy this array of bytes. In other words, it wouldn't really call the destructor on the thing that we truly store inside. So we actually call it explicitly. So we explicitly destroy our concept polymorphically by means of the virtual destructor, then everything's fine. All right. Next thing, the copy operations. The copy operations are very, very similar to what I've shown before. I simply call clone, but this time I just don't get a new value as a return. I simply say where it needs to go. So please copy into my buffer. I pass my own buffer as an argument to this clone function. And again, I implement copy assignment in terms of copy and swap, which again is super simple and definitely correct in this case. And there's not a lot of things that you could do to optimize this, to make it better. This is fine. All right. The last two functions are the move operations, which, however, you realize once we have this move operation, this abstract virtual function in the base class, actually turn out to be super similar. I move this other into the buffer. This will call the move operation here. And again, I swap the byte buffers. Copy and swap is truly kind of a safe way to do that. All right. Let's talk a little bit about buffer size and alignment. I agree that it's not a beautiful thing to have this in the class. It's like a fixed thing. If you have something that's a little bigger, then this class cannot be used, and there's no way that you can adapt this from outside. So kind of a logical choice is to actually move this into a template header for the shape class. So now we're actually able to configure the shape for a specific purpose. So we can have different buffer sizes, we can use different alignment. That's nice. Yet, of course, and you're correct if you would argue about that, there's more we could do. So for instance, we could actually also think about using dynamic memory and static memory in a mixed form. That's something that you could configure by means of simply stating we have a storage policy. So from the outside, somebody now tells us how the thing needs to be stored by means of calling new or make unique, or by means of some static buffer. You can actually configure this from the outside, which, by the way, because I'm a design pattern aficionado, it's a design pattern. It's the strategy design pattern. And it has a special name. We also call this policy-based design, which is the name that Andrei Alexandrescu suggested in 2001 when he tried to to some extent, port all of the classic design patterns to templates. Policy-based design is pretty much the same thing, just in the template world. All right. So this is definitely a nice idea. This gives us the ability to do a lot of beautiful things, like, for instance, providing some dynamic storage policy, a stack storage policy, perhaps a hybrid storage sheet, which allows us to differ. If it's small, then we store it in a buffer. If it's big, we allocate dynamically. Nice. And we could use them by just specifying this as a template parameter. So shape 1 uses dynamic storage. Shape 2 uses stack storage, and there may be a third shape that uses hybrid storage. Nice. However, although this sounds super nice, although this sounds like the way to go in the end, mixing these very different types suddenly becomes quite interesting, quite challenging. So now we have 2 different types, one that uses dynamic storage, the other one that uses stack storage. And we have to still make copy and move and all this stuff work. And basically, we can mix all the different options with all the 4, so to the 2 copy operations and 2 move operations. That's actually definitely beyond what I want to talk about. This is what I would usually recommend as don't do that. This is horribly complicated, and this definitely destroys the entire impression of type erasure. Once you try that, you will never use this technique anymore because it's so absolutely difficult. It really is difficult. And so now this discussion would definitely dig too deep. We would have to think too much about many, many details. And of course, you do remember what happens if you dig too deep. Yeah, because I believe you do remember what happened to the dwarfs in Moria. So digging too deep is not particularly healthy. So, however, we have indeed improved performance quite a bit. We have improved performance by approximately 10%. And I should state that I actually didn't create a lot of new shapes all around. This is kind of just having the static buffer and using it by means of a static buffer. Many people report that it can be so much more if you constantly create new objects. I know, I didn't know why somebody was laughing. 10%. We're actually bickering about a single percent in C++. So 10% is huge. By just writing a wrapper, by just having a static buffer, you actually gain 10% total performance in potentially an entire application. That's amazing. And it actually didn't take so much work. All right, so this is definitely something that you should consider. Why doesn't standard function do something like that? Well, probably because of the problem that I just pointed out. It's very hard to configure this for all possible cases, make it interchangeable. It really is a mess. There will be, however, I hope so, eventually an in-place function in the C++ standard. So something that is perhaps using static memory. I hope so, because there is a lot of options that might be interesting. All right, there's one more thing that I want to show you. Manual virtual dispatch. And this is definitely a thing that I now combine with some other idea, because I believe once you've seen that, you will definitely use this technique. This is way too powerful, way too good to miss. And the motivation is that we now have this wrapper we could use to write functions that just draw anything. I pass a shape, and this would draw it. So right now, we would pass a shape, probably by a constant ref. If you now in the main function pass circle and square, this will actually compile and it will work. So you've written a function that takes any shape and will do something with it. I'll draw it, for instance. This will work, this will compile. But for every call, you will, based on how we now implemented this, potentially allocate dynamically. So if you do not use the SBO solution, then this might potentially do an allocation and the copy operation too. So this wrapper might be a little too expensive for what you have in mind. What you might be interested in might be more like a type in a direction of a string view. Something that represents the thing but doesn't do a copy. Something that doesn't own. something that is way more lightweight and therefore does not cause a lot of overhead. So that's exactly what we now write. We write a non-owning abstraction, a non-owning type erasure wrapper. And that hopefully is pretty fascinating, because it will be just one slide of code, nothing more. However, I totally admit it's maybe the toughest thing that you've seen here in this session, but okay, it is not that bad. I should actually look at this positively. So this shape constref, first of all, takes, as all type erasure wrappers, a templated constructor. It's the same thing. So we take a shape t, but this time, as it's supposed to represent a constant reference to shape, it takes a const reference to shape t. Okay, now I do the thing that is probably something that you will feel to be absolutely amazingly horrible. I add a data member in form of a void pointer. A void pointer. Yes, I totally see the looks. I totally see what you're thinking. Now the guy's gone mad. Okay, no. This is actually perfectly okay. Don't leave now. Don't throw anything. I will fix this in a second, but this is now exactly what we need. We need a pointer. We don't want to create any overhead by having base classes, as we don't want to allocate anything. Now, this is the only thing that we can use, a void pointer. But, of course, we don't want to use this void pointer as a void pointer. We want to use the actual thing. And so here's what we do. Okay, sorry. And, of course, we initialize our data member shape by means of the address of shape. Okay. Now we add another data member. A data member that I, for syntax reasons, first abbreviate as draw operation. A draw operation is a function type for a function that returns void, and it takes a void const star. And then I have a data member called draw. That is a function pointer. So this function pointer now needs to be initialized. And that function pointer is supposed to draw the shape that I store inside. How do I initialize this data member? By means of a lambda. I write a lambda. A lambda that takes a void const star and performs a static cast to a shape t const star. And that's possible. Within the constructor, I am absolutely certain, 100% certain, that the given type is of shape t type. So I know how to get back from the void pointer. I know for certain what I have to do in order to go back. This is what I do. I convert the reference and pass this to the draw function. Now, whatever needs to be done at this point. This lambda is stateless. And because it's stateless, I actually can convert it to a function pointer. That one thing that I know that this lambda can become, so the one thing that I could use is a data member, and so I can initialize my data member by means of the converted lambda. Oh, nice. And now we are almost done. There's just one thing that you need to add. Again, a hidden friend that actually allows me to trigger this polymorphic behavior from the outside. A draw function. That was the convention, all the examples. A draw function that takes the shape const ref, reference to const by value, this doesn't matter so much. And we actually trigger the draw function. So please draw the thing that we store. And the thing that we store turns out to be a shape t. Absolutely amazing. Most importantly, this little abstraction is totally non-intrusive. You can add this anywhere on the fly, wherever you need abstraction for a set of types. Now, with a certain set of operations, you can just add it. You don't have to change any other existing code. And this makes this so amazingly valuable for any kind of interface. So it really is kind of a consequent extension of classes like string view, span, etc. It's a little more complicated on your part, but you see it's not particularly long. And it's always the same. It really always is the same. You just replace draw by any operation that you need. All right. So performance-wise, this manual virtual dispatch, so writing these virtual functions with this technique yourself, because this is what you do, actually has a interesting performance effect. Clang doesn't like it so much, but GCC does. Really, GCC actually speeds up quite significantly. Clang probably, it just doesn't like it. And now, of course, here's the big question. If I combine the small buffer optimization with this manual virtual dispatch, what do I get? Okay. It didn't turn out to be faster in my implementation. Perhaps I did mess something up. I didn't find any reason. Perhaps it's also a little too complicated. Perhaps the compiler cannot optimize so aggressively anymore. I don't know. So the combination didn't turn out too well, but definitely is still reasonably fast. So to summarize, Type Erasure is first a template constructor. All Type Erasure wrappers have this, plus a completely non-virtual interface. So the Type Erasure wrapper itself, somewhere inside in this nested hierarchy or in the function pointers that we store, it's kind of a virtual interface, but it's inside. And we combine these couple of design patterns in order to make it work internally. And I believe it's definitely one of the most interesting design patterns today. So Type Erasure significantly reduces dependencies. It enables value semantics, what we just do today in C++. This is the thing. It improves performance, potentially quite a bit. It improves readability and comprehensibility. And please do not think about the implementation. It's inside the wrapper. Okay, they're a little messy, but outside, amazingly beautiful. It eases maintenance because it's easier, absolutely. And it's for good reason, the default choice for dynamic polymorphism in many other languages. C++, we do this ourselves. In other languages, you get this by default without even realizing. Okay, that's it. Thank you very much for attending. Are there any questions? And I do have a mic in case you have questions. I believe this is better for any recording.
I noticed on your implementation with the buffer that it looks to me like your implementation of the move construction was actually copying, because you moved from a const object, I think.
The move construction of the buffer it really moves the inside. So it moves, so say you have a circle inside, it would move the circle. If the circle cannot be really moved, okay, there is not a lot you can move. But if you do, say, we have a polygon which stores its std vector of points. If that's what you store inside, then you would actually move the vector. That's the point. I do, however, not really. I cannot do anything else. You're right. Okay. Then one more question.
Do you recommend implementing this Type Erasure on your own, or using a library?
That is a good question. So should you roll this on your own, or should you use a library? There's actually a couple of libraries around. To mention a few, there is Dino, written by Louis Dion, which is a GitHub repository. There is the Zoo library, written by Eduardo Madrid. And there's also something in the Boost libraries. The last thing I showed, this is something I feel you should roll out your own. It's 20 lines of code. They are fairly simple. You basically cannot mess things up. And it's always the same. Yeah, you copy and paste this, adapt a little bit, it's done. This is something that you please roll your own. If you, however, have complex things and you do not want to do all of the stuff yourself, then perhaps you can use a library. I still feel it's reasonably simple that you can roll your own. But of course, it depends. The answer that nobody wants to hear, I know. Okay, then, thank you. Enjoy your evening.